So these operating systems which support multi-user, they are called as multi-user multitasking operating system. Okay, so normally the operating system is further uh, categorized into uh, single user, single task. Okay, single user, single task operating system, multi user, single task, multi user, single task. Then we have um, single user multitask, single user multitask, and then we have multi-user multitask, multi-user multitask. So these are all the categories of the operating system that we can use or define. So which the name itself says that the operating system supports only one user, and at a time it will take only one task or one program. So you give the program for execution. Until that program is executed, the operating system will not take any other program. So this is very simple operating system. Here we have single user. That means it does not have a concept of multiple users. Only one user can log in, but it accepts multiple processes to be multiple applications. Here task means application. Okay, multiple applications can be executed. In this case, multiple users are supported, but for every one user there is only one task that is supported. So this is only for the purpose of categorization. As such, there is no operating system which can be categorized into this particular category. Then we have this multi-user multitasking operating system, the complex of all the four, where it supports multiple users and each user can assign or create multiple tasks in the operating system. Okay, so let's understand what does this multitasking mean. Okay, so normally for the purpose of understanding this multitask support or multi-user support, we need to understand that operating system normally what it does is it divides the time into slots. So like slot 1, slot 2, slot 3. Like this, it divides the time into smaller values of time. Let's say, for example, some 10 milliseconds. Yesterday we discussed about 10 milliseconds time, right? We will try to understand why Linux, uses this 10 milliseconds. So this is 10 milliseconds. This is 10 milliseconds. Like that, it divides the entire time into 10 time slots, 10 millisecond time slots. So what it does is there is a functionality called scheduling functionality. So what does the scheduler do is it maintains what the scheduler does is it maintains different processes in the system. That means the process management module is running some complex algorithms to take multiple processes into the system. So it is capable of creating multiple processes. So like we discussed in our basics class, if any program has to be executed, that program has to be stored sequentially in the memory. So let's say that means I have program 1, program 2, program 3. Okay, so there are three programs that are that the operating system has simultaneously taken. So what it does is it assigns this 10 millisecond time interval for these processes P1, P2, P3, like that. It will assign 10 milliseconds. This, what I am talking, is just an example of multiple multitasking functionality is executed. This is, the complexity is more than what I am trying to explain. Okay, so it assigns 10 milliseconds to this process P1, it assigns 10 milliseconds to this process P2, 10 milliseconds to process P3, and like that for each process it assigns 10 milliseconds. Now there are three results that are possible, multiple results possible. uh, Results could be like, given process, let's say P1, needs some 50 milliseconds for completing its task. P2 needs some 5 milliseconds for completing its task. And this P3 needs, it's a biggest, so it needs some 100 milliseconds or 2000 milliseconds for the purpose of completion, executing the task. So how this 50 milliseconds, 5 milliseconds or 1000 milliseconds is calculated is based on the program, the instructions that are written for this processes. The number of instructions are calculated based on the instruction set architecture of the processor and how much time each instruction takes to complete. So addition of all these sum of instructions will result into this time. That's the assumption, that 50 milliseconds, 5 milliseconds, 1000 milliseconds. So what this scheduler does is, first it will allocate this program to the processor. That means it will copy, it will store the start address of this program into program counter of the processor, and it will ask the processor to execute. So the processor will start executing this program, and the 10 milliseconds, which we saw yesterday, that the timer is generating a 10 millisecond interrupt, that means hardware interrupt to the processor. So now the process P1 is under execution by the processor. How can the processor be communicated with? Two ways. One way is you assign the program for execution. Another way is you generate an interrupt so that the processor interrupts, and then the functionality of that interrupt service routine is executed. Now, at this 10 millisecond, there is an interrupt generated. Now, tell me, where is this interrupt landing? Yes, and where is the ISR implemented? The ISR is implemented in the scheduler. Now, the scheduler will see whether this process is completed or not. It will see the state of this process. Now, since the state of this process is not completed, it will put this process into backstage. That means it will put in, it maintains different data structures. Let's say it maintains an active processes list. Okay, then it maintains a deferred processes list, and then it maintains waiting processes list. Let's assume that it maintains these three lists. Initially P1, P2, P3 in the active processes list. P1 is here, P2 is here, P3 is here. So initially P1 is given for execution. P1 will start executing, and at 10 millisecond interval the processor is interrupted because of timer, and then the scheduler will start executing. It will see the state. It sees that P1 is still executing. There are multiple processes, P2 and P3 are waiting for execution. So it will push this particular process into deferred state so that it gets into this list, and then P2 is now assigned for execution. Is it clear? Now P2 will start executing, and P2 will need only 5 milliseconds for sorry, P2 will need only 5 milliseconds for execution. So when P2's 5 milliseconds is completed, sorry operating system will come into picture at the fifth interval where the process is completed. Now since it is completed, it will move P2 out of its list because it is completed, and then it will push P3. Okay, now P3 will start executing, and again after 10 milliseconds the interrupt comes, the scheduler will get executed, it will see P3 is still not completed, so it will put the P3 into deferred list and it will put P1 into active list because it is still not completed and it needs CPU cycles for execution. So can you see how this scheduler is executing? So the processes are assigned, operating system is maintaining all these processes in the memory, and each process is maintained with a state. Active state, in this example, it is maintaining active state, defer state and wait state. Okay. Now let's assume the P2 process, which normally takes 5 milliseconds, has an instruction to wait for the data from a device. Okay, that's what it is doing within that 5 milliseconds. Now there is no data in the device. What will happen is this P2 state will move from active state to wait state. Wait state means it is waiting for the data from a particular device, input device, output device, whatever. Okay, normally input device, let's take input device. And since there is no data and the process cannot go further until the data is read, it will be pushed to wait state. So in this mechanism where the scheduler is depending on this timer to schedule the next set of processes, in that functionality this wait queue is not in picture. Okay, now, if the device which this process is waiting for has the data, what does it do? It will generate an interrupt, and that interrupt will land into device driver's interrupt service routine, and it will publish to the operating system that it has the data. As soon as it publishes, operating system will go to the wait queue and figure out what are all the processes that are waiting for the data from this device. So since P2 is here and it is waiting for the data from the device, it will be pushed into the active list because it is now ready to execute. No, scheduler will not be in picture now. The scheduler will come when timer interrupt comes, right? Now, the interrupt that we got is from the device. So the device driver will read the data and it will tell the operating system that it has the data to be read. Okay. And when the scheduler is hit, then it will see that the processes which are waiting for the data from a device are ready to be executed. It will push that particular process to active list and it will get chance for execution. It can go to defer if the process did not complete in 10 milliseconds. No, 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 no. The data from the device is coming when the data is available. Okay, it is coming from the device, but while the device is generating an interrupt to the processor was executing something, right? It was, let's say it was executing P3, and within that 10 millisecond time slot, the device has interrupted. So look at yesterday's discussion. What was happening yesterday? The process was executing. Processor is executing some process. While it is executing that process, device has generated an interrupt. So it has stopped executing the process, then it has come to that particular interrupt vector table or interrupt table which processor defaults to. From there it went into operating systems interrupt management code. It executed device drivers interrupt service routine. Device has read the data and it has said I read the data, and then it has to go back. The processor has to go back in the same stage, and the processor will then continue executing the process. It has to be in a proper manner. It cannot be like a scatter gather kind of functionality. Yes, so P3 will continue to execute where it stopped from, and when the scheduler, the 10 millisecond timer scheduler is triggered, the scheduler will move the process from active state to defer state. Who is moving the process from one state to another state is scheduler. The process itself won't go into certain state. Are you understanding? No, 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 no. It won't. How will it go into deferred state? Processor does not have any control on these states. These are actually maintained by the operating system. How does processor know the state? What do you mean by both the tasks running parallelly? Processor cannot execute more than one task at a time, whether it is operating system or it is the one process will be executed by the processor. If it is multi-core, since there are four virtually divided or physically divided processors, four processes can execute simultaneously. But at a point, only one process is executed by one core. Yes. For the question, timer. What is? I didn't understand. Why does timer come into picture? No, no, no. Timer is a hardware. It is a completely different hardware. The job of the timer is every 10 millisecond tick, it will generate an interrupt. It doesn't, see, that's an independent entity, man. While your left hand is doing something, your right hand could be doing something else also, right? I didn't say that you said, somebody said that, interrupts will be must. I didn't say interrupts are must. I said the interrupt when it is coming, how does the interrupt handle? Somebody was saying maybe you only said that interrupt is must. I didn't say interrupt is must. Who will push into defer state? Question is that. And who is executing the scheduler? Who is executing the scheduler? Processor is executing the scheduler. How did the processor execute the scheduler? Using the interrupt mechanism. And who is maintaining this particular complete list? It is the scheduler. And where is the scheduler? It's in the operating system. And what is operating system? It's just a program. No, 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 no. I'm, I'm not joking. I'm serious. So, see the state of these processes are known only to the operating system, and very specifically it is the scheduler, and very specifically to this particular process management block. Okay, so where is my diagram? Ayo. Okay. Okay. So, what happens is the processor, all it does is it executes the program from memory. If you give the program counter and say that you execute this program, it will execute from that memory, or it will execute if there is any interrupt. The service routine is executed from that interrupt. That is all the processor will do. Okay, now the question is, when the interrupt comes, okay, and the processor, it interrupts, that means it stops executing the program that it is currently executing from memory. It will enter into the interrupt service routine, it will execute. So yesterday I had drawn this diagram. So we said this is the memory and this is the program that is available, right? And then we have the processor, and we had some diagram like this, where we had this programmable interrupt controller, and we said when this line is active, it is jumping into interrupt vector table, or whatever interrupt vector table, where there are 100 instructions like this, and from here it has gone into operating systems interrupt management code, and here the device specific interrupt service routine is executed. Once this returns, right, once this returns, the interrupt management code will blindly return back here, and from here the processor will come back. That means processor will know that the device, this particular line is handled properly. So what it does, it will again, what, let's say that it interrupted the program execution here, it will go ahead and continue to execute this program, rest of the program, wherever it stopped, it will go back there and it will start continue to execute this process again. That is how this processor is designed. Okay, so in our example we took p3 currently executing. So this p3 was executing it, let's say it started executing at this interval, at 10th interval, 10 millisecond interval, and we took three processes. Process 1 was 10, process 2 was 5. So let's say that process 1 10 milliseconds is over, and process 2 started executing. Since it is only 5 millisecond, at third millisecond it waited for the data from the device. So now process 3 will start executing from 13th millisecond, right? It after 13th millisecond it went to 18th millisecond. That is, in another 5 millisecond the device started interrupting. Now it generates an interrupt, the interrupt comes at 18th millisecond, the processor will stop executing and do this job, all this functionality it will execute. And so let's assume that this particular device, all this complete execution took another 2 milliseconds for the processor. So at 20th millisecond it will continue executing from this stage p3. Okay. Are you understanding? Okay, now it continues to execute. Meanwhile, there is another guy who is continuously generating interrupt at 10 milliseconds, right? So this interrupt is again an hardware interrupt. So after completing this interrupt and this interrupt is active, it will go execute this interrupt because it has more priority than executing this process. If your question is, okay, P3 is currently executing, the device has generated interrupt, it has processed it. Now the processor is about to go back and execute from P3, and immediately this scheduler has come into picture, right? When scheduler comes into picture, it will put this P3 into defer state, and whatever P2 which was in wait state, since the data is available, it will put P2 into active state and give the processor for execution. Okay, now your immediate question will be, how come P3 will be given for P3 will be deferred? It did not get the 10 milliseconds. That will be your question. Is it correct? Yes. So this scheduler will actually does not bother what has happened with the system within this 10 milliseconds. It will give fair chance to everybody. Whether within this 10 milliseconds a device has interrupted or the process got interrupted because of device, it doesn't bother. It will simply schedule the next process for execution. What we discussed is round robin scheduling for the purpose of understanding how this works. Okay, now there are multiple parameters added for the purpose of scheduling. Now, you may get different doubts on this particular discussion, right? So, a process, okay, you can use this time share for the purpose of giving fair chance to each process. Now you will get doubts, what if a program is needs to be executed immediately? Then the concept of priority is also given. Okay, so like this there are different parameters that you can program in the scheduler, and the scheduler can be executing complex algorithms for giving fair chance to the processes and also considering the priority. Okay, so round robin is one example where the processes are put in a queue, and then the processes is given process each process is given certain time slice or time share is done. 10 milliseconds, 10 milliseconds is one example that we have taken. So that is a circular list where all processes are put. It will move from P1 to and n, let's say P3, and it will again go from P1 to P3 continuously until the three processes are completed. So there is round robin algorithm, then there is priority algorithm. Algorithms based on priority. There are algorithms based on round robin and priority. There's so many algorithms are there. So the main logic here, the main intention of explaining this is to understand how multitasking is done. Okay, so the processor is not capable of multitasking. It is the operating system which is giving an illusion that there are multiple applications running in the system, but at a given point of time processor executes only one process. Is it clear? That particular process can be an application given by the user. It can be operating system which is executing. It can be a device driver code which is executing, or the interrupt service routine as a matter. Is it clear? Is it clear or completely clear? Okay. Hmm. Yes, we can discuss. Yes. Okay. So this is one way of this is the mechanism of time sharing, where there is an interrupt based time is managed or maintained. So if you precisely see how much time each a particular task is given, or how much time that the operating system is taking to do time sharing, if you do all these calculations, then you can identify what is the performance of an operating system. So if the scheduling algorithm is not taking much time, if the algorithm is running at order of 1, right? O of 1. I hope you guys know what is this O of 1, right? Order of 1. More Linux kernel scheduling algorithm you has this particular execution time order of 1. Okay, so within a deep standard time, within the given standard time, it will identify the process for the execution. So that's the way the algorithm is, right? So the time sharing actually done by the operating system. Okay, now let's add more complexity to this. Okay, my Intel processor is an 8 core processor. How many? Let me check. CPU. It will show. Okay, it does not have. So let me see. Yes, this is Mac. Yeah, this is Intel. The Power PC is gone, man. It's very old. What are you talking? It uses Intel. No, that is E5 A7 is for iPhone, and the latest they have designed one processor, one Mac. I think latest Mac is based on A5. I don't remember, maybe or may not be. So if you see there is this CPU, right? It is not showing how many CPUs are there in this. Okay, the reason I am saying complexity is if you have a multi-core processor, that means you are handling more than one processor, right? So if it is a 4-core processor, the same scheduling algorithm is executing on 4 different processors: 0, 1, 2, 3. Okay, so each processor can execute process simultaneously. So if P1 can be executing by 0, P2 could be executing by 1, P3 could be executing by 2, P4 can be executed by uh, third CPU. Right, now the complexity of the operating system is further increasing, right? So here you can have multiple processes which are time shared. Here you have multiple processors which are simultaneously executing. Imagine the kind of accounting that it has to do and the kind of management it has to do. It has to first know whether the processors are idle. If the processors are idle, it can move a process to a new processor. Okay, this will execute simultaneously. Okay, the processor is executing this. Now the scheduling algorithm will run on each processor, and the scheduler has to know, okay, whether this is ideal, can I schedule one more process? This is ideal, can I schedule one more process? So look at the complexity, right? So this discussion is about time sharing. How does the time sharing happen, and how does operating system do the time sharing functionality? So one famous operating system which come under this particular type of operating system is Unix or Linux operating system, where they support multiple users and each user can assign multiple tasks. Okay, so even to support multiple users, it uses this concept of multi time sharing. Okay, is it okay? Is it clear? No, 10 millisecond is independent of users. So multi users are managed by the operating system. So if you go deep, right? So each user is creating processes. Okay. If you remove user, so 4 users, for example, 4 users have created for example, like this. User one has created 5 tasks or processes. User two has created 6. User three has created 10. Right? User four has created 15. Okay, if you remove this user, okay, and only calculate the number of processes, it is about 10, 25, 30, 36 processes. So for the scheduler, it is 36 processes. You understood, right? So for the user will feel that his program is executing or his program is given priority. Other users, even though they are logged in, they are not executing. But every user will get the same feeling because 10 milliseconds is negligible, right?